Good morning there and welcome back. So, you have started watching videos on mathematical foundation robotics, and today we are studying the introductory dynamics, robot dynamics. Why introductory? Because we are learning how to model a tooling robot manipulated dynamics. But this is good enough to extend. The principle will be same, and you can extend it to any industrial robot. And why dynamics? Just a quick recap, because we want our model to be more perfect, eh? um, and the trajectory following by robot would be much better compared to resolved control. Okay, and in that context we studied that we will be talking about Lagrangian dynamics, okay, because it is easier based on energy and you know easier to model in the sense that this is not error prone. Okay, so steps are there that you will have to first make the robot frame of reference, means where you can represent the robot. Here we are assuming, for the again simplicity, that entire robot link's mass is lumped at one end. Okay, and actually this can be relaxed if you have a finite element software to model, but um, you will hardly achieve much in doing so, but you will invite definitely complexity. So that's the reason we are assuming that lumped mass concentrated here. And you see, this is my frame of reference. Okay, so this is link 1, L1 of length L1 and having mass M1, and this is link 2 having length L2 and mass lumped mass M2. So this is our actually Lagrangian equation of motion, which we are applying here. This is Lagrangian principle from Newton's second law. You can derive this equation. This is giving relation between cause and effect. So this is the torque. Okay, that means if the torque is the cause, then you will get effect as a motion. And if manipulator desired motion is required, you require to generate a torque that will be causing that motion. Okay, so L is actually Lagrangian function, which is nothing but the difference between a system's kinetic energy and potential energy. And this system consists of two links, okay, having lumped mass M1, M2, having length L1, L2. So first what we'll have to do, you have generalized coordinates theta I. Here it is 2 only, theta 1, theta 2. If it is 6 link manipulator, it will be theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. As simple as this. So once you compute L, then you actually differentiate that, partially differentiate this function with respect to the generalized coordinates derivative, and you also subsequently differentiate that with respect to time. Okay, and also you just differentiate that link length L, that is Lagrangian function L with respect to generalized coordinate. And as you will see that this is nothing but corresponds to the energy created by system kinetic energy in the system potential energy. So step by step we are actually progressing, and we have made a first kinematic relation. Then link 1, its kinetic energy is half mv squared, so m1 L1 theta 1 dot square, as simple as this. And systems, the link 2, the kinetic energy is half m2 v2 squared, and we have figured out v2 squared like this. Here what we have, without any step jump, we have minutely shown you everything. Okay, so you have now got a link 2's kinetic energy as well, which is half m2 L1 2 square theta 1 dot square plus half m2 L2 square inside bracket theta 1 dot square plus theta 2 dot square plus twice theta 1 dot theta 2 plus m2 L1 L2 cos theta 2 inside bracket theta 1 dot square plus theta 1 dot theta 2 dot. So this cos theta 2 actually is nothing but this is cos theta 2, right? You know. Huh? Isn't it? Huh? So cos theta 1 plus theta 2 plus sin theta 1 plus theta 2 will give rise to cos theta 1 plus theta 2 minus theta 1. So theta 1 is cancelled, so theta 2 only remains, and that's why it is this. Okay. So let us now move forward. So once we have K1, K2, then total kinetic energy we can calculate. Total kinetic energy, okay, total kinetic energy equals to K1 plus K2 equals to say K, okay. So this actually will have to add these two. So this will be half M1 plus M2 into L1 square theta 1 dot square plus half M2 L2 square theta 1 dot square plus theta 2 dot square plus twice theta 1 dot theta 2 dot, okay. So plus M2 L1 L2 cos theta 2 into theta 1 dot square plus theta 1 dot theta 2. So you are also advised to take your to open your notebook and do with me, so that you will realize completely and also will be able to check my mistake if there is any. So this is the total kinetic energy of this system. Okay. Now we need to calculate the total potential energy. Now we need to calculate. We need to calculate total potential energy of the two-link manipulator system. Okay. So how to do that? You see, I will draw it for you very in a simplified way. Okay. So this is L1, L2, this is theta 2, this is theta 1, and this is L2, and this is M1, M2. Okay. And this is gravity. Okay. So gravitational force is acting in this direction, in the negative z direction. So potential energy for link 1. Link 1, what it will be? Minus M1 G L1 cos theta 1, isn't it? So this is L1, this is the lump mass, so you need to have this. What is this? This is, you need to have this distance. This is L1 cos theta 1. Consider this triangle, right angle triangle. So cos theta 1, L1 cos theta 1 is this distance. So M1G and this distance. This is the potential energy of link 1. Similarly, potential energy for link 2 will be equals to minus M2 G L1 cos theta 1 minus M2 G L2 cos theta 1 plus theta 2, isn't it? Because now we are talking about projecting also this one here. So this one plus this one. So this plus this. So they, you see, in link 2. So this distance plus this is actually this distance. Okay. So this is the potential energy for link 2. So now we are in a position, so total potential energy will be equals to this plus this, so minus m1 plus m2 g L1 cos theta 1 minus m2 g L2 cos theta 1 plus theta 2. Okay. So what is L? L equals to kinetic energy, total kinetic energy minus total potential energy. So now bringing back from last page, total kinetic energy we have deduced. So it will be m1 plus m2 L1 square theta 1 dot square plus half m2 L2 square theta 1 dot square plus theta 2 dot square plus twice theta 1 dot theta 2 dot plus m2 L1 L2 cos theta 2 into theta 1 dot square plus theta 1 dot theta 2 dot plus m1 m2 so this minus is there, so minus minus it will be plus only. Okay, so this is plus m1 m2 g L1 cos theta 1 plus m2 g L2 cos theta 1 plus theta 2. Okay, so once you have got L, now it will the formula will start singing. So what you will have to do, you will have to partially differentiate this function with respect to generalized coordinates velocity, right? You will have to figure out this, which will be equal to, you see, I am quickly writing it down. You can easily do it. L1 square theta 1 dot plus m2 L1 square theta 1 dot plus theta 2 dot plus twice m2 L1 L2 cos theta 2 theta 1 dot plus m2 L1 L2 cos theta 2 dot. So once you have found this, so you'll have to just differentiate with respect to time again. So that's the formula. Equals to m1 m2 L1 square plus m2 L1 L2 cos theta 2 dot plus m2 L2 square plus twice m2 L1 L2 cos theta 2. So this is after simplification and collecting all the terms which are associated with theta 1 double dot. So angular acceleration. Okay. Then you have m2 L2 square plus m2 L1 L2 cos theta 2 theta 2 double dot minus twice m2 L1, L2 sine theta 2 minus M2 L1 L2 sine theta 2 dot squared. So please check. So you have, and you'll have to put it because we'll use it. So from our, so once we have got this, directly from our Lagrangian equation, I am ready to get an expression for tau 1, okay, immediately, right? So as you know, so theta 1 dot ddt of this minus will be tau 1, okay? Isn't it? So, and we have all the materials now. This one, this one we have derived. This one also we have derived, and now we are ready. You see, this one we also have, and then this is also we have, and I will have to of course figure out this one before writing. I need to have this. Maybe here I will write so that you will be able to appreciate. Small, then del L del theta 1 will be equals to minus M1 plus M2 G L1 sine theta 1 minus M2 G L2 sine theta 1 plus theta 2. Okay. So in this formula everything is there, all I required. So I can immediately I can write. So I will be starting writing from here. Just collecting those terms, I can write down torque. See, this is the magic. L1 square plus M2 L2 square plus twice M2 L1 L2 cos theta 2. So this is our associated with theta 1 double dot, the angular acceleration. Then M2 L2 square plus M2 L1 L2 cos theta 2 double dot minus twice M2 L1 L2 sin theta 2 theta 1 dot theta 2 dot minus M2 L1 L2 sin theta 2 sin square plus M1 plus M2 G L1 sin theta 1 plus M2 G L2 sin theta 1 plus theta 2. Okay. So immediately you got, okay, 1. Then similarly you can actually just repeat the same thing. That will be equal to M2 L2 square and then ddt of equals to m2 L2 square plus m2 minus sin theta 2 theta 1 dot theta 2 dot. Okay, and then immediately you can also calculate so you see, the more we are actually approaching towards the end link, what you are observing that things are, the expressions are getting simpler. Okay, for link 2 is the end link, so expression is simpler compared to what you have. So this is a observation I want you to make. So immediately, so this is obtained now, so you can hence talk to L1 or L2. Talk to will be actually, you see, L2 square plus M2 L1 L2 cos theta 2 sin theta 2 sin theta 1 plus theta 2. Okay. So this is very, very interesting observation, isn't it? You see what we have. You see, now again we have the manipulator. So lumped mass is there, and you see this is one torque tau 1 expression, this is torque tau 2 expression, what we have, and they are all in terms of, this is say x, y, these are all in terms of the generalized coordinate. This is theta 1, theta 2, generalized coordinate, their acceleration, their velocity, some angular acceleration, angular velocity, because we have revolute joint. Okay. Now you will have to see and appreciate that when we are talking about this tau 1, we have so many lengthy terms which consist of, you see, the inertia. This is, by the way, this is called what? The inertial term, okay, inertial force or torque. So this torque consists of, this is mass related thing, you know, mass and length related, and some cosine term is there. So this one, inertia, and multiplied by theta 1 double dot inertial torque. This is due to motion of link 1. And now you see, this is due to motion of link 2. This is inertial torque. And then this is called Coriolis torque. And this is called centrifugal torque. And this is called gravitational torque. So all kind of torque is, because you know two links are moving and there are coupling effect, means the link 2's effect also, it is moving with link 2, coupling effect is there, so the expression carries all the information. Here also you see torque 2 carries all the information. You see the torque 2 is also experiencing inertial torque from link 1 motion, inertial torque of its own motion, centrifugal torque, okay, centrifugal torque for its own motion, and this is gravitational torque. So if we just try to write down now this 2 in my next lecture, what we'll do, we'll try to now dissect and see the anatomy of these terms and their influences in dynamics, and we'll try to write down in a couple form, that means in a matrix and vector form, so that we can easily program it and we can easily understand all the effects. Okay, and next class we are going to do this, and we will also learn what is Coriolis force, what is centrifugal force, what is inertial force, all in detail. Till then, stay tuned and stay safe.